Alrighty, hello everyone, and welcome to my video on stoichiometry, one of everyone's most favorite chapters when it comes to chemistry. The purpose of today's video is to discuss what exactly a mole is, talk about how to calculate molar mass, how to start the three-step process known as stoichiometry, and kind of what the applications of that are, which we did in our lab. We're then going to talk about things like limiting reactant and percent yield, which is a useful tool for chemists to use as they are doing their reactions. Finally, there's just two final topics that I'm going to talk about that are kind of tangentially related. The first is percent composition and how we can use that to our advantage. And the second is for my honors class, we're going to be doing the hydrates. So this is just calculations based off of the lab that we did, and generally explaining what exactly happened during the lab. So without further ado, let's jump straight into what a mole is. So we have a mole here, we have our avocados. What exactly does all this mean? Um, and what I did in class is I talked about the example of a dozen, because a dozen is something that we can understand. We've seen it. Here's a dozen eggs on our screen, and a dozen just means that there's 12 of something. So if I have a dozen eggs, I have 12 eggs. If I have a dozen elephants, I have 12 elephants. That word dozen just means 12 of something. And what that is it's a count. It says that I have a certain amount of whatever it is you're talking about. 2 dozen means I have 2 times 12. That's the amount of eggs that I would have. Um, and the important thing is that this is not the same as weight, which I will call mass. But these are two different ideas. And we can tell that a dozen eggs weighs less than a dozen elephants because an elephant individually weighs more than an egg. And as we kind of transition from a dozen to a mole, what's important to also know is that different atoms have different mass. Here's my hydrogen atom. If I have one hydrogen atom, it's got a mass of 1.008 daltons, it's our unit. So one atom of hydrogen has this mass. An atom of mercury has a mass of 200.59 daltons, which we'll get to grams, we'll get there. So if I have 10 atoms of hydrogen or 10 atoms of mercury, the mercury is going to weigh more even though I have the same amount of them. And that's the gist. That is the relationship between amount and mass. And this entire chapter is about conflating the two. If I have this amount of atoms, how much does it weigh? And it depends on the different atoms themselves. And if you are just interested, of course, why is this different? Well, there's more protons, all this stuff from way back in the beginning of the year. More protons, more electrons in mercury. Those protons have mass, etc., etc. Okay? So that brings us to this concept known as the mole. So it is a quantity, and instead of 12 of something, I have this very, very, very large number, 6.022 times 10 to the 23rd, which is Avogadro's number. So we've been using moles a lot. And what it just is, it's an amount of something. So it's like counting off by dozens. If I have 12 eggs, I have 1 dozen. 2 dozen is 24 eggs. Now, I haven't focused on, how many molecules and how many atoms and all that stuff. But what you should know is that if I have a mole of something, it's just a count. It's telling me how many atoms I have, or molecules, or eggs, or elephants, or anything. If I have 1 mole of eggs, I have 6.022 times 10 to the 23rd eggs. And this is known as Avogadro's number. It looks like avocado. It's why you see all this avocado paraphernalia. It's called a mole, which is why you see mole paraphernalia when it comes to chemistry a lot. This is what the guy looks like. Here's Avogadro himself. He didn't actually invent the number. He just postulated that it existed, and someone honored him by naming it the number after him. So this is Avogadro's number, and it just tells me when I have 6.022 times 10 to the 23rd of something. In our case, we're going to be dealing with atoms. 6.022 atoms of hydrogen, for example, is 1 mole of hydrogen. So if we take an atom, for example, here's a mass of carbon-12. Um, and if we take this unit from the Dalton, which we started when we first did the periodic table, and I talked about just what an atomic mass is. And I said, here's our atomic mass, 12.011. And I kind of introduced this unit of a Dalton, which is kind of standardized around, 1 proton is 1 Dalton, etc., etc. And if you actually do the math, and what makes this so nice is if you take the mass of a Dalton, convert it into grams, you will find that the ratio between the Dalton and the gram is exactly the same. So what that means is that our molar mass is effectively the mass of the atoms, but if you have a mole of them. So what do I mean by that? This is the first kind of, what do I mean by that? This is the first kind of foray into what we've done and what I'll ask you about. I will ask you some general questions about just what a mole is. That, hey, it's a count. It's something. It's how many things you have. All right. So what this means is that if I have a single atom of carbon, it has a mass of 12.011 Daltons, whatever that unit is. But if I have 6.022 times 10 to the 23rd atoms of carbon, that mass is going to be exactly 12.011. And our unit for this is 12.011 grams, right? Grams, that's something that you put on a scale. You measure out in grams, and we've done this in our lab. We went to a scale or balance, and we measured out 1 gram or 2 grams or something like this. But if I had 12.011 grams of just pure carbon, I would have exactly 1 mole. So when I attach the unit of this, and I haven't been a stickler for grounding, and I apologize. You know, that's one of the things I will work on is being, hey, this is what it must be, and setting those rules and all those boundaries. But 12.01, for example, grams per mole. And I've said this unit all the time. What does this mean? What this means is if I have 12.01 grams, I have exactly 1 mole. The opposite's also true. If I have a mole, I would have 12.01 grams. Those are also true. And if we want to put this at the level of understanding, that means that if I have 6.022 times 10 to the 23rd atoms of carbon, the mass of all of these atoms will be exactly 12.01 grams. That is what this tells me. That if I have this very, very large number of atoms, and I put every single one of those atoms onto a scale or onto a balance, I will get that mass of 12.01. Alright? And whenever I say grams per mole, the example that is always the most relevant to a lot of you as you're taking your driver's test, as you're taking driver's ed, is always going to be miles per hour. If I'm going 60 mph, miles per hour, that's 60 miles in 1 hour. Per is usually divisible by 1. So 60 miles per 1 hour. And that's what I want us to keep in mind. Or that means in 1 hour, if I take 1 hour, I'm going to be going 60 miles. In physics, you're going to be dealing with velocities, with speeds, probably being meters per second. But you're going to be dealing with this concept of per. Grams per mole, miles per hour, meters per second. Okay? That's just the general concept of what a molar mass is and the understanding behind it. Now, how do we actually solve for molar masses of various compounds? Here I have kind of set up where I have my periodic table on my left or my right, and we're going to start calculating some molar masses. All right. And what we have to first do is figure out what atoms are actually in this molecule. So here's CO2, carbon dioxide, and what I can tell is that there's one atom of carbon, because again, there's a subscript that's invisible, and there's two atoms of oxygen. So this is what this looks like, CO2. And my subscript tells me that there's two atoms of oxygen. So how do we actually calculate what the molar mass is? Well, first we're going to go and we're going to find carbon. And we're going to see that carbon has a molar mass of 12.011. I'll stick to one decimal place for now. I would like two for my honors class, just to make um, our results a little bit more accurate. So every carbon atom has a mass of 12, or a mole, I should say, has a mass of 12.01 grams. There are 1 mole of atom of carbon, so we're just going to get this and put this at 12.01. 12.0. I did just say that I was going to use one decimal place for now. 12.0. Now the oxygen, we go and we find my oxygen. We're going to round this up. I'm going to round this to 16.0. But because there's two atoms of oxygen, we're going to have 2 moles of oxygen. And we're going to get 32. And we're going to add this up, and my unit's going to be 44. Now again, here's my unit. Here's where this comes in. 44 grams per 1 mole, which we can also stylize as grams per mole. These are equivalent. You can write it either way, either thing like this. These are equivalent statements. Grams divided by mole or just grams per mole. It's the same thing mathematically. Okay? So if we move on a little bit, move my screen over here to give us some more room. What happens when we have parentheses? This is kind of the biggest, you know, let's just like curveball that you can get, because most of these, even if you get something like sucrose up here, C12H12, it's just really, again, C is going to be 12.0 times 12, H is going to be 1.0 times 22, gives us 144.0, which gives us 22, and then oxygen is just going to be 16 times 11, and that's going to equal what, 176, I think. And then you just add all this up. If my math is wrong, then just assume you have a calculator. Um, 2 carry the 1 there. That's a 4. 342.0. There's my quick math right there. So it's just, that's easy. It's just more math. I could throw something in the thousand at you, and it's the same process of just doing this. The one thing that really kind of trips us up is anytime that we throw in parentheses into the mix. And I'll start with an easier example here. We're talking with magnesium hydroxide, MgOH2. Now, what this looks like is I have an Mg with a 2 plus, I have an OH with a minus, and an OH with a minus. That's what this looks like. How do I know that there's 2 of these OHs? Because this thing is outside of the parentheses. If I just had, NaOH, for example, then it's just 1 of each. But because I have this group, this polyatomic ion here, this OH, it sticks together. It's like a big atom that sticks together. That 2 outside the parentheses tells me that I have 2 of these OHs, which means that the amount of oxygen I have would just be my subscript, which is a 1. Remember, I'll draw on the 1s here. So O would just equal 1 times 2. There's 2 atoms of oxygen. Same with hydrogen. 1 times 2, 2 atoms of oxygen. And once you get to this point, then it's the rest, then it's the same as what we've been doing. So magnesium over here, we're going to go find magnesium. So that would be Mg would be 24.3, and there's 1 magnesium. Oxygen 16.0. Remember, there's times 2 of them. And hydrogen is going to be 2.0, or yeah, 1.0 times 2 gives us 2.0. So we add up all these, and we're going to end up with 24.3, 32.0, and 2.0. We add all this up, and we get 58.3 grams per mole. All right. So the only tough thing with this is that you have to make sure that this 2 is only being applied to the oxygen and the hydrogen. And on another example where it gets a little bit more difficult, and something I saw in some of the quizzes, would be something like E or something like H over here. So I'm not gonna do the math on this, but I'll show you how to set it up. So let's look at this bit right here, NH42. What this looks like, if we were to draw this out, would be NH4. And technically, there's a plus sign on there because this is a polyatomic ion, so there's a charge. And we can see here that there's 2 nitrogen atoms and 1, 2, 3, 4, 5, 6, 7, 8 atoms of hydrogen. And how do I know that? Because NH4, 2. When you have a parentheses outside of something, like let's say you had 2x plus 2, what do you always do here? You distribute it. It's just like algebra. 2x plus 4, you distribute it. So my subscript of my nitrogen is 1. So 2 times 1 equals 2 nitrogens. And 2 times 4 equals 8 hydrogens. So that's just the one thing to keep in mind. I'm going to give you polyatomics. We had some in the lab where you had to calculate the molar mass. You didn't have to do any parentheses, I don't think, in our lab, but I'm probably going to give you an example with parentheses and some kind of polyatomic like this. All right, so if we're setting all this up, we're going to take nitrogen, find nitrogen 14.0, 14.0 times 2, hydrogen, again, 1.0 times 8, sulfur, 32.06, call that 32.1 times 1, and then oxygen would just be 16.0 times 4. And you do all this, you add it up. That's molar masses. And you need molar masses for pretty much everything. You're going to need molar masses for any type of stoichiometry. Any type of these unit conversions that we're going to be doing, you need molar masses. And most of the time, I'll give you a hint. I might say, hey, you need this, especially for my honors class. I'm not going to give you these hints. You need to know that you have to take the molar masses. Like, it's not just going to be, oh, don't forget your molar masses. It's not going to just be given to you like that. You're going to need molar masses of whatever we're converting between. That's just how it's going to go. So our first of our 3 stoichiometry steps, and I'm going to put it all together, but what we have, and I have the stoichiometry steps. The first thing that we're going to be doing is let's say I'm converting, doing the stoichiometry conversion, and let's say I have examples of it like this. If I have an equation like this, and I say I have 20 grams of aluminum, and I'm going to ask how many grams of aluminum oxide are going to be produced, right? So I have a chemical reaction. I have a certain amount of one of my reactants. How much am I going to get? You need to know, how much am I going to get? I mean, think about it. If you have a piece of rock and there's some gold in there, I want to know how much gold am I going to get? How much of this ibuprofen, how much of this medicine am I going to create? That's the whole purpose of this. So my 3 steps, of which here's our first 2, or 2 of the 3, is converting from the grams of whatever I'm giving into moles of whatever I'm given. And I have here just the examples, and kind of this is your tips and tricks. Here's the step-by-step process. For scholars, I'm more likely just to write it out and to give you these steps on a test, and break it down instead of doing it all in one go. Like, you would get these individual steps. You won't get, you have to use the molar mass. You have to use the you're not going to get that. Obviously, I'm not going to give you that. That's not. You have to know how to do it. But we start out with grams of something, and we have to convert it to moles. So we have a mass of something, and we're basically asking, I have this amount. I have this mass. How many atoms does that mean? How much of this stuff do I have? How many atoms do I have? So, if I have, you know, 50 50 pounds of eggs, how many eggs do I have? That's what we're at really asking. If I have 50 eggs, how many eggs do I have? If I know what the mass of each egg is, that's really what we're going for here. So our first step on this journey is, again, we need our molar masses. Because again, if we're converting between grams and moles, you need something that combines the two, which is what a molar mass is. Which tells me if I have a dozen a mole, what is the mass of them? That's what this means. So let's say I have 88 grams of carbon dioxide. And if you notice, the way that I structured this, um, I use these molecules here are the same that I use in at least for my scholars class, in this one, the molar mass one. It's the same molecules on purpose. One of the things I kind of noticed some folks did on their quiz is I had the numbers, I had you guys calculate the molar mass, and then you calculated it again. The purpose of it was to use it up here, or to calculate it up here, and then use it down here, because it's a multi-step type of question. All right? Um, so keep that in mind. If I'm asking for a molar mass, most of the time I'm gonna be using it, and somewhere else. All right. So here's our starting value of 88 grams of carbon dioxide, and I like to put it over 1 to show here's my numerator and here's my denominator, to keep things up like that. I can use it, square it off like this, just showing us up top. I've shown that, but what we want to get to, and where is this M? What is this M doing? I don't know. Goodbye, M. What I want to get at is what a molar mass is. And just to reiterate this, what a molar mass is 44 grams of CO2 per, here's that per again, 1 mole of CO2. That is what a molar mass is. It's literally the mass of a mole. Molar mass. How much mass per 1 mole? But we can also say it and write it in the opposite form. If I have 1 mole, I have 44 grams. Just like the example. If I drive for 1 hour, my distance will have been 60 miles if I'm driving 60 miles an hour. That's what that means. And I've explained, the math behind it with these units, but the gist of this is that if my unit up here is grams of CO2, that I want to choose this right here. Start color coding this. I want to choose this because here's my grams of CO2 and here's my grams of CO2. The unit on the top and the bottom have to be the same. 44 grams of CO2 per 1 mole. Again, these units right here must match. Grams of CO2 and grams of CO2. All that's left is to multiply. So we're going to multiply the top numbers. That's just going to be 88 times 1, which equals 88. And we're going to multiply the bottom numbers, which is 1 times 44, which equals 44. And then right here, 88 divided by 44 just gives us 2. What is my unit? Moles of CO2. 2 moles of CO2. And I want to get away from if you do this, you have to divide. If you do this, you have to multiply. Because what happens when we start, adding more and more type of things? Like, I don't want you to get into that habit, because when we start doing, we might do other unit conversions in this year, you're going to need to keep track of these units. When you do dimensional analysis on the final, you're going to have to keep track of your units. It's such an important skill to have, especially when we're going to convert it from milligrams and kilograms. I think like half of you, I said 0.46 milligrams, and you multiply by 1,000. If you keep your units in track, that's not going to happen. So there's one example. I'll do another one. I guess I'm going to have to clear the screen. So, I forget what that M was for. So MgOH2, we had a molar mass of 58.3 grams per mole. All right, so here I have 29 grams of magnesium hydroxide. Set it up over 1. Set this one up. Grams of magnesium hydroxide. Grams of MgOH. I'll say this again. I will say this again and again and again. The unit on the top must match the unit on the bottom. The unit of these must be the same. Because then they're going to cancel each other out. Grams, grams, gone. Get rid of the G, the grams. Alright, and this is where my molar mass is. This 58, please don't do this either. I've seen people where they put the 58.3 on the top. This 58.3 is glued to the G, to the grams. If that's what you wanted, think of it G for glued. 58.3 always goes with the grams. Because it's grams per 1 mole. It's always going to be 1 mole. 1 mole. 58.3 grams. So we get 29 divided by 58.3. What do we get? I could type. I could type. We get this. Decimal places. 0.50 moles of MgOH2. This is always going to be the first step in our stoichiometry. It's going to be starting with grams of whatever we're starting with and converting it into moles. There's step 1. Alright? And we're going to come back to this worksheet. We're going to come back to right here. But that's step 1. Step 2 is to convert moles of Y to moles of X. And that's what this worksheet's all about here. I'm going to start out with this equation here. This is the only time that we need to use the chemical equation itself. And so what does this look like? If I have what this equation says, my coefficient of 4, and we'll, I know that this is a, ionic solid, but it works fine for us. This is our chemical reaction. This is what a coefficient tells me, that there's 2 Al2O3s, and notice that we have the same on both sides. We have the same on both sides. This is what this tells me. So this is our equation visualized. So what if I had, double the amount or something? There's always a ratio. No matter what in this reaction, I will have 4 atoms of aluminum to 3 molecules of O2. 4 atoms of aluminum to 2 molecules of Al2O3. If I have 4 moles of aluminum, guess what? I'll have 3 moles of O2. This is a set ratio determined by the coefficients. Anytime I do this reaction, it's going to be in some multiple of this. If I double the amount of aluminum, I double the amount of oxygen. I would have 8, I'd have 6, and I have 4. It's always in this. This is the lowest common denominator, this lowest possible ratio. And that's why we use these coefficients for a conversion like this. So this is our step 2. Is once I've gone and I've calculated, where is it? That I have, what did I say? 2 moles of CO2. I have 2 moles of CO2, and I now have to go and convert this. I think I have CO2 in one of these equations, do I? I do. Yeah, so let's use it like this. Well, CO2. So if I have, I'm just going to ignore this question for now. So let's say I gave us a question and I solved this one, and I said I have 2 moles of CO2. And I need to convert. I have 2 moles of CO2, and I want to convert this. How much methane caused that? How much CH4 caused that? I'm converting from moles of CO2 to moles of methane. Well, keep my 1 here. Again, mole CO2, mole CO2. And let's say I want methane, I want CH4. Guess what's going on top? Moles of CH4. So when I visually draw this reaction, look at these wonderful hydrogen atoms. When I visually draw this reaction, the amount of CO2 that I have is going to be equal to the amount. Notice not mass, the amount. The amount of molecules, the count. If I have 1 molecule of CO2, I will have 1 molecule of methane. If I have 15 molecules of CO2, I will have 15 molecules of methane. If I have 2 moles of CO2, guess what? I'm going to have 2 moles of CH4. Why? Because my coefficient's going to be the same. I take this 1, I take this 1, 1, 1. The math simplifies real easily here. We would get, 2 over 1, which just equals 2 moles of CH4. And this gets, a little bit more complicated when we start introducing something that's not going to be the same ratio, which is why I like this reaction here. It's why I did this reaction here. So if I have 3.2 moles of Al, how many moles of Al2O3 will be produced? Well, let's start. I start with 3.2 moles of Al. I'm going to move this over. I'm going to put this over here. So 3.2 moles of Al. Put it over 1 to keep my numerator and denominators. Well, guess what? Moles of Al. Guess what's going to go here? Moles of Al. And what am I trying to find? Moles of Al2O3. If there's something that you need to just force yourself to memorize, like the unit here, these units must match. These units that I put in green here, they must match. And when I say unit, I mean including what the molecule is. You can't put moles of Al2O3 through different molecules. It'd be like saying I have a dozen oranges and a dozen apples. Even though the dozen's the same, the apples and the oranges are not the same. Okay? This is where we use my coefficients. Here's my coefficient for aluminum, 4. My coefficient for Al2O3, 2. And now we simplify. 3.2 times 2 equals 6. 1 times 4 equals 4. 6 divided by 4 equals 1.5. I have 1.45 moles. This is 6.4. Excuse me. That seems too easy. 1.6. There we go. Perfect. 1.6 moles of Al2O3. There's my second step. There's my second step. And all this is 7.4 moles of Al2O3. This doesn't, it can go in reverse. How much of my reactants did I start with? Well, that means I got 2 calculations. 7.4 moles of Al2O3. And what goes on bottom? Guess what? It's moles of Al2O3. And let's just say I want to start, I'm going to do my aluminum here, Al, moles of Al. Again, my coefficient, 2. Now the 2's on the bottom, and 4. And this is going to give me, 14.8 moles of aluminum. That's how much I started with. I could do this the other way. I can do any type of reaction. I could say if I had 0.6 moles of O2, how many moles of Al do I need? Any type of reaction here. If I had 0.6 moles of O2, and I want to convert that, how much aluminum do I need for my reaction? Oh, moles of O2. My coefficients are 3 and 4. You get, what, 2.4 divided by 3? 0.8? Just, this is not one of these questions. That's not what this question is, so don't get confused by that. That's why that's not the answer. Please don't get confused by that. But it doesn't matter if you're going from product to reactant. You can go from reactant to reactant, product to product. It does not matter. It's the same idea. That's the second of our 3 calculations that we're going to be doing here. The third is then we're going to convert from moles of X to grams of X. So this is question number 2 here. And again, we need our molar mass. So H2O2, to our molar mass, we get 34 grams per mole. You do these enough, you get to know oxygen and hydrogen, or you know those ones by heart. So if I have 2.0 moles of H2O2, I'll put my 1 here. Here's my box again. This box, the units must be the same. Moles of H2O2. Moles of H2O2. What number goes with it? Remember, this 34, the G glued. 34 is glued to the G. It's always going to be per 1 mole. 34 grams per 1 mole. Always per 1. Always per 1. Please, those are the things you need to memorize. You need to know that. You need to know what this means when I say grams per mole. It's great that you can calculate it, but you need to know what it means. That will help you with these setups. Because you also need to memorize this little box here. Moles, H2O2, moles of H2O2, 34. 2 times 34, this will just give us 68. Yep, mass checks out. Grams of H2O2. So I don't want you to just remember. So at this time I memorize. Step 3 I memorize. Or step 3. Step 3 I multiply. Excuse me. Step 3 I multiply. Because yeah, I'll give you these steps, but I could throw other things at you. There's a lot of math on here. Just to say, oh, step 3 is multiply. Not always true. We're going to be doing more stoichiometry. When we get to thermodynamics, like enthalpy of reactions, where you're going to need to convert the moles because we're going to have molar enthalpies. That comes up. Like, this concept of a mole doesn't just go away. Right? So I have 175 moles of CI4. That would be carbon tetraiodide molar mass. I'm too lazy to look it up. I apologize, or to do it. So don't be scared by big numbers either. So let's just say CI for molar mass is 519.6 grams per mole. Oh my goodness. So 175 moles. That's a lot of carbon tetraiodide. And I put this on purpose. The second letter is an uppercase I, just to remind us that this is iodide. This is chlorine. Please know the difference. Please don't mess that up. Moles here. Moles here. CI4 1. 519.6. Fun big number. A 90,930 grams. That's a lot of grams. That's a lot of grams. And that's the final of our third steps. Those are the third steps. And now what I'm going to do is put it all together. Alright? Before I get to that, though, I'm going to give you a question. And let me just pull it up. Somewhere on your test, somewhere you will have something in milligrams or kilograms. And you need to know these conversions. Like milligrams, kilogram, those are so fundamentally used. Like milligrams, hey, cool. How much medicine? 200 milligrams of ibuprofen. Milligrams are used commonly for things like medicines. Kilograms are used a lot. The bag of Epsom salts come in kilograms. When you have a lot of stuff, you need kilograms. Grams just are too small. All right. So please, what this means: 1,000 milligrams in 1 gram. This A grammatically means 1. 1,000 milligrams, 1 gram. 1 gram, 1,000 kilograms. Same with kilograms, except now it's 1,000 kilograms, or no, 1,000 grams per 1 kilogram, or 1 kilogram per 1,000 grams. So when I gave you a question on your quiz that said, oh, 46 milligrams of caffeine, the amount of, what you should be doing first is converting this from milligrams to grams. 1,000 milligrams in a gram. 1,000 milligrams, 1 gram. Because again, here is my box. Zoop, zoop. Look at that. Milligrams, milligrams. There's my box. mg, mg. This gets us 0.0046. Nah, get rid of that 0. There you go. 0.046 grams. Then you can do once it's in grams, you do you do the same thing that we've just done. You can just do this additional step here. Guess what? You're gonna get something in kilograms or milligrams, or milligrams or kilograms. You're gonna get something like that. You have to know those conversions. All right, and I'll show you an example of this later. Okay, so with all of that said and done, let's put everything together. Stoichiometry. So I will refer back to this slide a lot just to remind us of our steps. All right. For scholars, you get it written out like this. It'll be written out: step 1, step 2, step 3. I will show us how to do it all together at once. So if you're in scholars and you want to do the whole math, be my guest. Just say, hey, like, here it is. Here's my final answer. That's fine. You can do it in step 3 and just leave the other 2 blank. Don't care. I'll show us the combined method here. Either method works. All right. So what we need to do is we need to first convert grams of Y to moles of Y. And how do I know what it is? Well, it's whatever I give you. 20 grams of aluminum. So 20 grams of aluminum. And this is not set up in the steps, but I'm gonna color code this. So my blue is just gonna be step 1. All right. So 20 grams of aluminum. All right. Well, I need to get my molar mass, so I'm gonna put my molar masses. I want aluminum and I want aluminum oxide. Alright, now you're going to have to calculate these. I'm going to look them up because I'm lazy. So let's do molar masses for aluminum. Aluminum would be... we'll call that 27. Make our lives easy. 27.0. We'll round up there. So aluminum will be 27.0. And Al2O3 will be 102.0 grams per mole. And I'll put the grams per mole here. So let's get back to our step 1. Remember, step 1 was these type of conversions that we did all the way up here. So that's just reminding us what we're doing here. So if I have grams of aluminum, put my 1 here. We're putting grams of aluminum. I'm gonna highlight the box here. Grams of aluminum, grams of aluminum. Just imagine that this is a lovely L. And what's going to go on top, or what's going to go here? Well, my 27, which is glued to the grams, glued to the G, 27, and 1 mole goes on top. 27 grams per 1 mole. 1 mole per 27 grams. Those are my equivalent statements. So I'm going to solve for this. It's going to end up simplifying to 20 divided by 27, which gives me, we'll take 2 decimal places on this, 74 moles of Al. Here's step 1. Step 1 done. Okay, let's move on to step 2. Now, this is, because my writing is so large here, I'm just going to kind of jot this out. So I'm going to be doing work down here, but I'm not answering part B. I'm not answering part C. I'm just doing my work down here because my writing is very large. So please, 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 I'm not answering these questions. I'm making this very explicit. I just need the extra space to do the different steps because my pen is very large and bulky. Okay? So let's move on to pick a nice orange for step 2. So we'll take this answer, and we're going to transport it down here. 0.74 moles of Al. And now step 2, we're going to convert from moles of Y to moles of X using the coefficients of my chemical equation. Now, what is my Y and the X, and what does that mean? Well, the aluminum, this is what I started with. So in this case, X equals Al, and Y equals Al2O3. And all this just means is X, or what did I put it here? No, I put it backwards. Sorry. My Y is aluminum and my X is Al2O3. The Y is just whatever I start with, whatever, I started with 20 grams of aluminum. My X is what do I want? I want the aluminum oxide. That's what I want. So I start off with 0.74 moles of aluminum. Put my 1 here, moles of Al. We're gonna draw in our little banana, or not banana. That's a box. On top, what I want moles of Al2O3. Alright. My coefficient of aluminum is 4. My coefficient of Al2O3 is 2. We're going to get 0.74 times 2 divided by, put this parentheses, 1 times 4. And that's just going to give us 2 divided by 4. You could have it same mathematical, but I'll show it out for us. 0.37 moles of Al2O3. Alrighty, that's step 2 done. My steps got messed up. There we go. Last but certainly not least, let me move this up and out of the way, is, where does 2 go? 2. Step 3. I should say that this is moles of Al2O3. So yeah, I did. I labeled it. So we're going to take my answer here, and this answer is going to go over here. 0.37 moles of Al2O3. And here we're doing these types of calculations here, which you can scroll back, you can go back in the video, watch that again. Just, I'm going to do it. We're going to put my moles down here on the bottom, my grams on top, my molar mass, my 102 is glued to the grams. 102, 1, and we end up with times 102. We get 37.74 grams of Al2O3. So it should make sense that we started with 20 grams, but our product, we ended with 37.74. So we started out with 20 grams and ended up with 37.74 grams. Now, it would make sense. This is a synthesis reaction that you're putting 2 things together. You're going to get a bigger thing. But some of our reactions, that's not true for things like a double replacement or a single replacement reaction. That's not necessarily true, or a combustion reaction, for example. There's our final answer, and here's our 3 steps to do this. I'll give you a second, take this in, And what I'm going to then do is I'm going to show you kind of the quick way to do this. I say the quick way, it's kind of the combined way. All right, so I'm going to scroll down here. I'm going to put my face up here. And I'm going to show us, not with this question. Again, I'm going to mark this one out. I'm not doing this question. I'm ignoring this question because I need the space here. So just please, again, I'm not doing this question. I'm just blacking it out, so I'm showing us the quick way for the question that I just did. So I started out with 20 grams of AL. I'm gonna do it like this. I'm gonna show us like this. I like to do it like this. It keeps it all in track. It keeps my numerators and my denominators. So this is just the same as saying, 20 over 1 times whatever. It just kind of replaces it. It keeps my numerators and my denominators in line. All right. Well, what I'm gonna end up doing is, well, I know my first conversion is gonna be from 20 grams of aluminum into the moles. So I'm going to color coordinate this. Here's step 1. Again, 27 grams, 1 mole. There's step 1. But if I calculated this, if I stopped right here, I'm going to get 0.7 moles of Al. But I can keep going. Because what am I going to do with this moles? I'm going to do this. I'm going to do this. This is what I'm going to do with it. No matter what number goes there, that's what I'm going to do. I'm going to take my moles of aluminum, which, shame on me for not labeling this, Al. Moles of aluminum right here, that's the same as the unit up here, which means that I'm still going to put 4 moles of Al, 2 moles of Al2O3. So I'm just not stopping. I'm doing the conversion that I would have done, but I'm not simplifying after every single step. It's the same conversion, just all in one step. Which means that if I did this math, if I stopped right here and I calculated this, what am I going to get? I'm going to get this. I'm going to get 0.37 moles of Al2O3. If I stopped right here. I don't want to do that. So I'm going to put in whatever I have here. I have moles of aluminum Al2O3, because look, grams of Al, moles of Al, moles of Al. So I'm left with just moles of Al2O3. 102 grams of Al2O3. And look, moles of Al2O3, moles of Al2O3. We're going to simplify this. We're going to get 20 times 2. I missed the 1. Doesn't matter. Times 102. Divide this all by 27 times 4. Let's put this in a calculator. 20 times 2 times 1 times 102 gives you 4,080. 27 divided by 4 goes 108, or multiplied by 4080 divided by 108. Pretty close. Pretty dang close. Now, why is this not exactly the same? It's because I rounded at each step here. I did some rounding. That's rounding error. I'm going to request that if you do it in the 3 steps, you probably shouldn't round it until the very end. But this is close enough, the rounding error. Right, 0.03. I'm not being a stickler on the units and counting that at this time, so that's acceptable. Both of these answers are acceptable. I'll let you take this in. Oh, I don't mean to do that. I'll let you take this in, kind of digest it. It's a lot here. All right. What I'm going to be doing, I'm going to do question number 3 right here. Because this one, oh, look at that. That's 4.5 kilograms. Now, you could 4.5 kilograms of NaCl. You could just convert this, well, 1 kilogram, 1,000 grams. Kilogram, 1 kilogram. There's my box. $1,000 grams. So that's 4,500 grams of NaCl. But here's something. Guess what? I'm going to include this calculation in my stoichiometry. I'm going to do it. I'm going to do it. So we got to find our molar masses. So let me do that real quick. I'm going to write that up. So here's my molar masses off here to the side. You're going to have to do molar masses. Anytime you're doing stoichiometry, you need molar masses. So let's start off. We have 4.5. No, actually, I want to erase this because I want to use the same colors as my last kind of section. So we start off with 4.5 kilograms, and I'm going to include the other conversion here. 1 kg, the one there, 1,000 grams, because now my units are in grams of NaCl. Now we go back to our steps. All right. What you might want to do here is, now that I've set this up, try this on your own. Try this on your own. Pause the video. Try this on your own. As I'm walking through it, oh, you're stuck or something, watch the video. Watch it as I go through this so that you are doing this instead of passively just listening. Try this with me. I started the setup. This is the new bit. The new part is the kilograms to the NaCl. And this question asks for each of my reactants, so I'm just gonna start with we'll start with 2Na. We're gonna start here by converting this to Na. All right. So do this with me. Just listening to this and not doing anything with it, you're just gonna passively do it. You have to practice it yourself. So if you want me to do the first one, if you're like, no, I still don't know what to do, watch me do the first one, and then do this with the second one. With, instead of Na, it's going to be CO2. Watch and learn. Do this with me. Don't just watch. That is not a good way to study. I promise you. Your brain will learn this more if you do it yourself. I know that I'm like already like 40 something minutes in and I'm making this plea, but it's a good strategy. All right. My first step here, convert grams of Y to moles of Y. Well, what am I going to do here? I need grams of NaCl, and here I'm going to start color coding this. So I need grams of NaCl. There's my box. I'm going to find 23, and these are all in grams per mole. Those are all in grams per mole. They're always going to be in grams per mole. So my 23 is glued to the G for 1 mole. Now I'm going to move on. I'm going to move on. Like, I'm not going to just simplify it after every single step here. I'm going to move on to the next step. Nope. Because now, what is my unit? My unit is moles of NaCl. Right? Let's go to step 2. Convert moles of Y to moles of X. What is my Y? Again, my Y is what I'm starting with. The Y is what I start with. NaCl. My X is going to be, in this case, Na. So we have moles of Na. So let me color code this again. But I use orange. There we go. Moles of NaCl. What do I want? I want moles of Na. There's my units again. There's my units again. Now what numbers go here? Coefficients, which are both 2. Alright, let's move on. Now my unit is moles of Na. I have moles of Na. I want moles of Na of X, 2 grams of X, using the molar mass. Okay. So, we are going to use red. Moles of Na. And what do I want? I want grams. Grams of Na. Here is our box of units. Again, top left, bottom right, same unit. Top left, bottom right, same unit. My 23. I hope you didn't make the same mistake I do. Oopsies. If you caught me, congrats. It was a test. That should be 58.4. So if you're screaming at your phone or your Chromebook or whatever, oh my God, Mr. Rady, you made a mistake. Yes, I did. Oops. I don't have the time to re-edit this. 1. And now here's my 23. Oop. Caught that mistake. Caught it before I finalized it. That's why you double check your work. So now I put all of this together here. Alright. So I'm going to do the top. Here's my top. I'm going to multiply through here. Take 4.5 times 1,000 times 2 times 23. Divided by bottom. 1 times not 23, but 58.4 times 2. Pull this up. 4.5 times 1,000 times 2 times 23. 207,000. Now remember, I'm starting with 4.5 kilograms. That's a lot of salt. So we should expect our answer to be pretty big. Just letting you know. 1 times 58.4 times 2, 116.8. 207,123 divided by 116.8. Final answer is 1,772.3 grams of sodium. Notice, I started off with 4.5 kilograms of NaCl, which is a lot. That's 4,500 grams. But of that, only 1,772 of it's sodium. Alright, let's do part 2. Or not part 2, but I'm going to do question number 2. Where instead, I'm going to put it down here. I'm going to leave this up. I want this as an example. I'm just going to erase all of this stuff so that I have the space for it. Alright. Cl2 is right here. It's got a little messed up here. A little laggy right there. But now I wanted both reactants, so I'm going to convert this and I'm going to do it for Cl2. So the setup actually starts the same. 4.5 kilograms of NaCl. I'm going to set this all up. 1 kilogram, 1,000 grams NaCl. The setup starts the same. And actually, it starts the same here again. 1 mole of NaCl and 58.4. Look at me getting it right. Grams of NaCl. Starts the same. But here's where it differs. Well, now I want Cl2. So moles of NaCl and moles of Cl2. So my coefficient is still 2, but my coefficient for my chlorine is now 1. And that's where things get a little bit different. And things continue to get different when we now take the 1 mole of Cl2, 70.0 grams of Cl2, our molar mass. Now, again, the only time that we use the coefficients is during step 2. This is the only time we use the coefficients. Any of the molar masses, so in step 1, Or in step 3, the mole amount's always going to be 1. It's one of those confusing things that I've seen happen. You always have 1 as your mole, because it's per 1 mole, per 1 mole. Say it again and again. The only time that the mole is going to be not 1 is coefficients, which is step 2. So these are things that you got to remember, things that you got to practice. The more and more that you do this, the more and more you practice this, the more and more you're going to get it. All right? And if we put all this together, we end up with, I'm just going to show us up here because I'm running out of room, 4.5 times 1,000 times 1 times 1 times 70, 315,000. So we have 315,000. Let me write that down. On the bottom here would be 58.4 times 2, 116.8. We do all this very fun math. You get 2,696.9 grams. Grams. That's a grams. And that's our stoichiometry. Two questions like that. And you're going to get on your test probably 2 or 3. Probably 2 or 3 of these, I would say. Honors, probably 4 actually, because there's 3 in the limiting reactant equation. This is what this involves here. Now again, you mess up 1 or 2 steps, you get partial credit. As long as you know what you're doing for 2 of the 3 steps, you get that partial credit. But this is a built-in, take the answer from this, take the answer from this. That's built into this. That's what stoichiometry is. It is a multi-step calculation. And we're bringing it all together for our test. All right. So now what we're going to get into is something known as reactant, and it's kind of the experimental part of of our chapter here, and where it really applies. So the limiting reactant is, think of it like this, and this is an example I used in class. If I'm making cookies and I need eggs and I need sticks of butter, right? If I have 2 million eggs but only 1 stick of butter, I'm not making 2 million cookies because I'm going to run out of butter first. That's the concept is you run out of one of your reactant. You just don't have enough to continue the reaction. That's all you can make. And so what we can use with stoichiometry, or what we can do with stoichiometry, is we can predict which of our reactants is going to run out, which will produce less product. Because you can't produce more product if you run out. You can't make the 2 million cookies because you're going to run out of butter. And so what we can do here is figure this out. And this is really kind of the final, I guess, hurrah of stoichiometry. And what you'll get is the way that the stoichiometry problems, for the most part, are going to be presented on your test will come in the form of a limiting reactant problem, which means that most of what you already have to do, I've already covered in this video. So what I'm going to go do is I'm going to fill out questions 1, 2, to already kind of show us where we should be. This is just an example, writing the balanced equation. I wish I had the time to bring that back. That's not something I would do. I would not pull something like that for us, as mean as I may be, not that mean. So you can look up this answer, and here's the answer here. I'm just going to rewrite it. What I'm going to come back is have the answer to 1 and 2. I'm not going to be doing the stoichiometry again. I've already gone through that. If you want, you can pause the video here. I'll write the equation up here. 3C2H3O2H. Yeah, very fun. Acetic acid. C2H3. Let me get this. I'll be right back. All right, so here's our equation. And this is a tougher one in terms of like the molar masses and the why is there a H3 and an H here. What I want to show from this more so is the concept of a limiting reactant. So if you want to, you can go and try your hand at this one. Just note that this would be C2H4O in terms of calculating your molar mass. All right. So this is definitely more of a challenge one. If you want to do question 2, all right. And what this means is determining the mass. It basically means convert grams of both of my reactants into grams of aluminum acetate, which is this big one. So one is going to be grams of um, C2H3OH into grams of AlC2H3O3. And then the other one's going to be grams of AlOH3 into this one as well. So this is a more involved one. This is definitely a challenge problem. So if you would like to do it, pause my video, go through it. I'm going to have the work done with the answers up here. All right. This is definitely more involved, but what this tells me, what I can do is look at the answers, and that's where I can make my comparisons and talk about limiting reactants. And before I do that, because I'm noticing reagent is equal to reactant. They're the same. Just they're synonyms. All right. So I'll be right back with these answers. Alrighty, that was a doozy. So take a moment, you can check over, look through what I've done. If you did this problem, you can check over it. If I have to write another C2H3O parentheses 3, it's not very fun. But it'd be like that. So here are my two answers. If I started with 125 grams of acetic acid, C2H3OH, and 275 grams of aluminum hydroxide, Al parentheses OH parentheses 3. These are the two amounts that I would end up with. I would end up producing either 141.5 grams of aluminum acetate, Al parentheses C2H3O parentheses 3, or 719.6 grams. Now, the 719, that's like my 2 million eggs. It'd be great if I could get there, but I'm not going to get there. I just don't have enough of my acetic acid, of my C2H3OH, because I'm only going to produce 141.5. So the amount that I'm actually going to produce is only going to be this amount. I can't make my 2 million eggs. I cannot make my 719.6. I can't get that full amount because I just don't have enough acetic acid. I don't have enough. I would need more grams of acetic acid to utilize all of my aluminum hydroxide. I'm going to have leftover aluminum hydroxide. So my limiting reagent slash reactant is going to be my acetic acid, C2H3OH. This will be the limiting. So it's always going to be the number that's smaller, the product that you get that's smaller. So you do all this, and I ask you, what's the limiting reactant? Well, what's the smaller number? That's what you need to get to. If acetic acid is my limiting, and I'm just going to put this, here's my limiting. The aluminum hydroxide over here is going to be my excess, which means that I have excess. I have extra of it. Okay? That's what this means. So the next part, just before I move on to percent yield, is going to be how much of the excess reagent will be left over after the reaction is complete. Now, this is something that I only did ask of my honors class, but it makes a good extra credit question for a scholars class. Just throwing that out there if that's what you're interested in. So how do I do this? Well, I'm only actually going to be producing 141.5 grams of aluminum acetate. So what I need to do is I need to see if if I only end up with this amount, well, how much of my excess reactant, does that use? It's not going to be the full 275. It's going to be much, much less of that. But how do we do this? Well, we need to do more stoichiometry. All right. We need to convert my 145 or 141.5, which is how much, that's how much I'm actually going to get, theoretically. We need to convert this into my excess reactant to see how much of it was actually used. So I'm going to cut to the answer. If you would like, we're converting from Al2 or aluminum acetate this to my excess to AlO3. So my final answer should be in grams of AlOH3. All right, that's what my final answer should be in. So I'm going to cut. You can check your work. Pause the video right now. When, 5 seconds or so, the answer, all that stuff's going to be up. All right. All right. I never want to write all these subscripts. Are so tough with the mouse. You can see the quality of my writing with all these is it deteriorates as I do this equation. But I get a final answer of 54.1 grams of aluminum hydroxide. So what this means is I started out with 275 grams, and I only used up 54.1 grams of aluminum hydroxide. And if 54.1 grams, that's how much aluminum hydroxide or aluminum acetate I'm going to get. This is all I can use up, because after I've used up 54.1 grams of aluminum hydroxide, there's no more of my acetic acid, so the reaction cannot continue. I can't get to that 19.6 grams. So the question does just ask how much of the excess reagent will be left. Well, it's actually pretty simple. I just take what I started with. I subtract how much I actually used. I will get my answer. 275 minus 54.1. So, all said and done, I have 220.9 grams of aluminum hydroxide left. And that, it's more stoichiometry. I like giving this type of question because it's stoichiometry practice. So, oh my god, goodness, this was a lot. So what I want to do before the last thing is just, this is what is known as a theoretical yield here. Theoretically, given the amount, if 100% every single atom reacted, and I was able to magically, nothing was lost, I would end up perfect 141.5 grams. I would have exactly that amount. But let's be real, that doesn't happen. Things happen. There might have been some leftover reactant. You might have been some extra water. Something can happen, and you're not going to get the full yield. You might get a side reaction. Yeah, something that you didn't think would happen could happen. Some of it might have, some of the calcium carbonate, it would actually dissolve. Very little of it, but some of it does. So what I want to cut to is something known as percent yields. So I'm going to come back up with this. I'm going to have this formula up, but what I do want us to keep in mind is that I have 141.5 grams of my aluminum acetate here. All right. So I'm here on WikiHow because it's a convenient image. Looks nice. And what this says, and it also just says here is how much you actually have versus the theoretically you could make, right? Contaminants, predictable problems, it happens. And the term yield, just what that means is, right, like you're yielding something from baking. It's different than a yielding in driving. It's this reaction, it yielded, it produced. That's kind of the synonym for it. It's how much was produced, the yield. It's just in a noun form. All right, so that's what that means by yield. So my theoretical yield for my last example was 141.5 grams of aluminum acetate. So let's say you did that reaction. You mix those two things together, and you actually only got. So this is equivalent to us in our lab measuring our calcium carbonate that we actually formed. How much of this did we actually form? And let's say in this reaction we formed 120.7 grams. The formula is pretty simple. We'll take the actual yield, which is the actual yield. This is what you experimentally measured in the lab. What your data told you, you calculated. All right, 120.7 divided by 140.5. Multiply this by 100 because that's what a percentage is. 120.7. That's not what I want. 20.7 divided by 141.5. And this gives us this. We multiply this by 100. 85.3%. It's pretty good. Pretty good. Now, why is it not 100%? Maybe some of my yield got lost. Maybe it was dissolved in water. Maybe I spilled something. Maybe there was still the calcium carbonate stuck to the sides of the beaker. I had to really clean those beakers because there was definitely still stuff that was stuck to it. And you couldn't rinse it out because it's not soluble in water. That's why it became a solid. So, but let's say, I'm just going to say this, it's possible to get over 100%. Let's say our calcium carbonate, let's say it was wet and there was water and that increased it. And let's say my actual yield, which is in this case too, was 174 grams or 170. You can get over 100%. That's right. It doesn't make sense. It means you messed up somewhere. Something happened, but it's possible. And it's about explaining why did I mess up? How can I not get this? I've done labs. I've gotten 400% yields before. I'm like, who, oh boy, that's not good. I messed something up. 400% yield. That's not good. Messed something up in that lab. That's what happens when you take analytical chemistry in at 8 a.m. in a dingy basement. You get 400% yield. All right. So this formula pretty easy. And what you're gonna get on your test, and I'll say this now. I know we're a while in. Um, you're gonna get some questions like why did I get 120% yield or something based off of the reaction that we did. You're gonna get something like this. Um, some kind of lab related question. Why did I do this? Why did I separate, like what was the point of that? You're going to get questions based off of the lab itself. So we can understand kind of the science behind it. It's not just going to be questions on the math. There are going to be some questions like what was the purpose of the separatory? Like why do we, what did the filter do? There will be some questions on that to understand what actually happened in the lab. All right. So there's two final things that I need to just finish up just for my pacing of this video. We have to finish percent composition and then for my honors class, the hydrate lab. So let me skip over to percent composition. Be right back. Alrighty, so here is percent composition. And I kind of threw this in here as a wild card because it relates to molar masses. And that's kind of why I wanted to throw it in. And we'll see an example of this and why this is kind of important. Um, as it turns out, it actually makes certain stoichiometry equations pretty simple, but that's not the case for many reactions. That's alright. It's fine. So we're trying to find the percent by mass. And one of the things that I just wanted to really to let you guys know is when I say percent composition, it's percent composition by mass. All right. I saw a few of us do this on our test, or on the quiz. If I give something like, let's just see, FeCl3, it's not FeClCl, Cl. Well, Fe is it's no, it's 25. percent, because it's 1 out of 4, that's not what I mean. This is by mass. Okay? It's that, not this. No, not that. Don't do that. All right? And here's an example that you can kind of go through. But what you basically do is you find the molar mass. So here's iron 3 hydroxide, Fe parentheses OH parentheses 3. And I've done all this stuff. We've gone through all this type of stuff before. They use 3 decimal places, which is crazy. But we've done this before, plenty of times. Go back to the beginning, go back to molar masses to see how to do this. But what we end up doing is dividing the part by the whole. What that means here. Well, here's my total molar mass of 106.87 grams. Of that 106.87, how much of it is oxygen? Well, here's my oxygen bit here. We just take the number here, 48, divided by the whole. 48 grams divided by 106.87. That is it. That is it. And then we can also see here if you're given a 16.0 gram sample, right? How many grams of this, which is the percentage, which is just 0.4491, right? That's what this is. Percentage, you just divide it by 100. You get the in decimal form. You just multiply 16, the sample size, by this number, and that gives you 7.19 grams of oxygen. So I'll ask you a question like that. How much of this, if I have a piece of, I don't know, aluminum hydroxide, how much aluminum is there in there? Like, let's say you want scrap metal, right? If I have a big rock that has some copper in it and some other junk, how much copper can I get? That's useful for things like mining. If we need copper or rare earth materials for our cell phones, how much am I going to get? How much of it am I going to get? That's why this stuff is important. If I got a big rock, how much rock of the element that I want am I going to get? So I'm going to go through question 1 here. Question 2, I'm not going to go through. But instead of this, I'm going to ask for the percentage of everyone. Which, right, when I say the percent composition, that's what I mean. I want each element. I want you to do this for each element. Okay? I want each element. So what I'm going to do here is I'm going to kind of go back to one of our earlier worksheets where we've already kind of figured out our molar masses. So let me go and do that. So we did part B, and I want to use part B just as an example here. We already did part B, magnesium hydroxide. We figured out 58.3 grams per mole is our molar mass. And if we broke this down, magnesium would have been 20, double check, 24.3. Let me make sure I don't. 24.3. Oxygen would be 16 times 2, which is 32.0. And our hydrogen is going to be 1.0 times 2, which equals 2. So to calculate the percent composition of each element, well, we take 24. So for magnesium, we take 24.3, divide it by the total, which is just 58.3. And we're going to multiply by 100. And that's going to give us 24.3 divided by 58.3. This mumbo jumbo long number. Give me a decimal place on this. 41.7. Alright, move on to oxygen. Again, we're going to take this number. We're going to take the bit of it. 32.0. We're going to divide it by 58.3. Multiply this by 100. 32 divided by 58.3. Multiply this by 100. We get 58.9 percent. And we're going to finalize with hydrogen. Take 2 divided by 58.3 times 100. And we get 3.4%. Now, if we add up our percentages, 3.4 plus 58.4 plus 41.7. Oh, what did I mess up here? It should be rounding error. What did I mess up? Let me. All right, I noticed an error. I swapped the 4 and an 8, so I had to do a quick cut. 41.7. Now, if we add up everything, 0.8 plus 3.4. Now we get 99.9, which that's rounding error. I rounded error. You know, that's 100%. There's our percent composition. Now, the one where we can go from this. Now, let's say I have a chunk of magnesium hydroxide. Let's say I have, just for example. Well, let's say, for example, I have 29 grams of magnesium hydroxide. How much of this sample is magnesium? If I did a reaction, how much magnesium could I get? Well, take 29, we multiply this by in our decimal form, which we'll just divide by 100. 0.417, and simply enough, 29 times 0.417, 12.09, 12.41 grams of magnesium. That's how much magnesium is in this. All right, there's our percent composition. You get something like that, make it fun, themed. I don't know, it'll be fun. You get some kind of percent composition question like that. If you are here for Scholars Chemistry, this is all that I will expect of you. I know this is a lot. Please, please, please practice this. That's the only way that you get good at this. Go through, do examples as I go through them. Check your work. Okay? That's the way that you do this. I've done plenty of practice examples here. Try them out. Do this, the examples by the examples. That's the best way to get good at this, is to practice it. I have a whole bunch of work on the master document that I put. Um, there's a lot of those extra worksheets there, just to practice it. Okay. If you're here for honors chemistry, the final thing that we talked about is a hydrate. And you'll get something that's just what is a hydrate, for example. Like what is it? Explaining it. You get something like calculating the molar mass of it. Like how do I calculate the molar mass? You're gonna get something like this. But what you're really going to get is you're going to get data. You're going to get data like this. It's going to look exactly like the lab, the same data. I'm even going to include it as here's my crucible mass and here's my, I'm going to give you the data. I'm not going to give you the how to do it. I'll give you the data. Here's the mass of the crucible in the anhydrous example or sample. You get a question like that. That's going to be what happens if there's too little or too much water, like some kind of application question to that. Some kind of lab question. This will all be in the study guide. I want to be as clear as possible with this, like what to expect, so as I make it. That's what you're going to get. And let me just walk you through this type of problem here. So we have nickel chloride dot XH2O. Please, this dot is not a multiplication sign. Please do not be the person that does that. It's not a multiplication sign. I say it again. I've said it many times. I put it in parentheses and bold. It's just the convention that we use for a hydrate. That's it. Okay? That is it. Alright. So, I'll walk us through this. Let me get to a place where I can write all this stuff out, and then we'll walk through this. Alright, so this is the type of data you'll get. If I give you if I decide, I actually thinking, I'm not sure, the crucible, you're just gonna have to subtract the mass of the crucible from the mass of the crucible in the anhydrous sample, and that's how you get the mass of the anhydrous example. But here's the example from the slides. And what I've also done, because we're dealing with grams and we need moles, guess what we need? We need molar masses. I've already calculated them. So that's why like you need to know molar masses. It's such a important part. Um, I'm not even gonna like ask you a molar mass question because it's just you just have to do them. Gotta know how to do them, and that's just you need to know how to do it. So here's kind of our data. So what we did here is we started with 0.470 grams of nickel chloride and .xH2O. And just a reminder, what this means is that in our crystal we have our nickel 2 plus, chlorine minus, and somewhere there is water that is attached and attracted to this because of those ion dipole bonds, because water is polar. That's why this happens, because water is polar. So I might ask a question about that. Like that's the type of content questions, like why does this happen, that I might ask you, and it throws back to other chapters. That's the type of question that you might get. And what we can do is, because these bonds are weaker, because they're intermolecular forces, we can burn them off, get rid of them, and basically dehydrate this by getting rid of the water. So anhydrous just means without water. So if we start with 0.470 grams of nickel chloride and we end up with 0.256 grams of, the only difference between this and this is the water. So 0.470 is what we started with the nickel chloride and the water, minus 0.256, which is the amount with, that's the amount of without the water. That's going to give us the mass of the water, 0.256. So the 0.470 is the nickel chloride and the water. The 0.256 is just the nickel chloride. So you subtract the two, and that's the mass of the water. Because that's the only thing that has changed. And so now that we have our mass of water and our mass of nickel chloride, we need to convert these to moles. Because we need to figure out the ratio of molecules. How many molecules of nickel chloride are there to molecules of water? And it's just like the example that I did with the coefficients. It's a set ratio. That's what this x is. It's a ratio. How many molecules of water per how many nickel chlorides? And when we have a ratio, we need moles. So 0.256 grams of NiCl2, convert it to moles. 129.6. There's our G for glued. And we're going to get some small numbers here, so you got to bear with it. 6 divided by 129.6. That's okay. Don't round yet. Don't round yet. You're going to round, don't round yet. Or, give me a lot. Give me enough. 197. That's probably fine. Honestly, that's probably fine. Alright, so that's the moles of nickel chloride. Of H2O. And by this time, like, you need to know how to do this. I'm simplifying it. You're in my honors class. I've done these plenty of times. Now, alright, give 1187. Or 1188. Alright. Moles of the H2O. And again, this is a proportion. This is it's a ratio. It's a ratio. If I have X moles of this, how much is this? So how I like to set this up is to think of it as a ratio. You've done this in your math class. Alright, so what this tells me right here is I have one, because remember there's no coefficient. My coefficient's 1. 1 NiCl2 per XH2O. And I need to find X. And this is equal to the amount of moles that we have, because that's the ratio. Moles is a ratio. Well, my moles of 0.00197 moles of NiCl2 divided by 0.01188 moles of H2O. Well, to solve for this, we basically cross multiply. We're going to end up with, mathematically, 0.01188 divided by 0.00197 equals x. We'll put this in our calculator. Divided by 0.12123. And boom, we get 6.03. What do you think we're going to round that to? 6. So we end up with our formula is NiCl2.6H2O. Or this would be nickel. Ooh, and don't forget the 2. Don't forget that. Remember that? Yeah, I took a point off for that on your lab. Why do I know nickel is... How do I know that nickel is plus 2? Well, chlorine's going to be minus 1. You needed to know this for the last test. It doesn't. You don't need to stop knowing that. You don't just stop knowing that. Chlorine's going to be minus. There's 2 of them. So nickel has to be 2 plus. Then even that out. Nickel 2. Chloride. Guess what? You're going to have to name something. Guess what? Don't forget the parentheses. You'll probably be a chloride. I'll probably be nice to you at least. Or I'll give you the charge or whatever. Nickel 2 chloride. 6, like a hexagon. Hexahydrate. There's my name. There's my name. And how do I calculate the molecular or the molar mass of this? Well, I already have nickel chloride. So that's going to be 129.6. Plus, well, I have 6 waters. So 6 times 18.02. 108.12 plus 129.6. So my total molar mass will be 237.72. 237.72 grams per mole. I mean, I could give you a hydrate in one of the other questions. There's, I can mix and match between hydrates and other stuff. How many moles of this do I have? Like, I can do all that stuff. Nothing's different. I think one of those problems like gave something like that. I think it was the percent composition one. But it gave you something like that. It said, what's the percentage, like I did in the lab. What's the percentage of water in Epsom salts? Same type of thing. All right. So that's our test. So here's your long video. Going through it. Practice, practice, practice. I'm gonna post some practice problems for this as well. This is how you get good at it, is you practice it a lot. So good luck with your studying. Let me know if you have any questions. We'll have our Zoom review probably, in-person reviews. We'll do all that fun stuff. All right. So take care. Have a wonderful time studying.